Okay, so the next theorem we look at is if f is continuous and increasing on a to b, then f has an inverse function, f inverse, denoted f inverse, make sure you have that on your paper, that is continuous and increasing on that same interval there, on the f of a, comma f of b. Now, we can also prove similar results for decreasing. So where this is increasing, same thing in the case for decreasing as well. And then the derivative of an inverse function. So this is the new portion. What we've done previously in this lesson has just been the review of inverse functions that we've done in college algebra and also pre-calculus. But now we're going to do the derivative of an inverse function. So it's going to be defined by this. If a differential function f has an inverse function, you can, sometimes it's called g, sometimes we use f inverse. And if the f inverse of g of c is not equal to 0, then this theorem, this definition is going to hold true. So the corollary to that is just we would plug that in for x, and we'll have the x value because we're more often than not, we work with the bottom one in terms of x. Okay, our first example we're going to do is we're going to do a three-part problem to this example. The first thing we're going to be doing is once we were given a function, we're going to prove that f has an inverse. Then we're going to state the domain of our f inverse. And then the last thing, we're going to find the derivative of our f inverse. So let's start with the given function. Let me do a different color. So f of x, this will be given to you. So f of x is going to be, let's see, the cubed root of 5x plus 2. Okay, first thing we're going to do is we're going to do the algebra behind it to find it, to see if f has an inverse, and find that. Okay, but before we go through that step, we want to prove it has an inverse. So we're going to look at this theorem, and it says it has an inverse if it's continuous and increasing, and we also said that's the same thing, continuous and decreasing. So what we've got to do is we've got to look at the first derivative and determine if we have that condition. So let's take our function, first of all, f of x, let's rewrite that as 5x plus 2 to the 1/3 power. And let's take the first derivative of that. Okay, you can go ahead and do that while I'm rewriting this. Okay, remember, so we're going to have 1/3, leave your parenthesis the same, minus 1. So what's 1/3 minus 1? Negative 2/3, and then we have to take the derivative of this inside function. What's the derivative of this? 5. Good. So, okay, which if I simplified this a little bit and cleaned it up, it would just be 5/3. Bring my 5x plus 2 to the bottom to rewrite it as positive. That's still to the 2/3 power. Now all we want to know, this is all positive values. So since it's all positive values, it tells us that it's going to be greater than 0. So f is increasing. Our original function is increasing from negative infinity to positive infinity. So therefore it's going to be 1 to 1. It has an inverse. This is going to tell us it has an inverse. Okay. Now we got to actually go find it. So now we're going to come back over here to our algebra step and find it. Okay, the first thing, rewrite it with y equals, and the next step you want to interchange your x and your y values and then solve it for y equals. Okay, so once we solve that, I get f inverse of x is equal to x cubed minus 2 divided by 5. Alright. Okay, so we can put this in our original function in our graphing calculator if we like and look at it to just see that the range of f is equal to all real numbers. So the domain of f inverse is equal to all real numbers. So we can use our theorem that our relationship that we have here to be able to answer part B. Okay. And using this information is the safest way to do it because we can rely on the given information because we calculated this. If we made a mistake of this and then tried to take the domain here, then we might get a mistake in part B. But if we use our given information and rely on our theorem, we can get a more accurate solution there. And what's our last part? Our last part is to find the derivative of our f inverse. Okay, so let me just state first of all that g prime of x is equal to 1 over f prime of g of x. Okay, that was given down here. That was our corollary 7.8. Now, let's make this a little bit more familiar to us. So if g is equal to the f inverse, okay, we let g be our f inverse, then this same thing can be rewritten as the derivative of our f inverse of x, which is what we're looking for, is equal to 1 over f. Remember, if we replace g of x with the f inverse, that would be f inverse of x. Okay, so this is what we're going to calculate here. So the derivative of f of inverse, if we let g be our f inverse, then we would plug g of x, let f inverse of x be our g of x here. Okay, and we're going to take this on the next page and actually calculate it. Okay, so from this point out, we're going to use this notation more often than not, but I wanted you to see the transition from the g notation to the f inverse notation, which they're the same thing, they're equivalent, but I wanted you to be familiar with both forms. Okay, just to have it set up on the next page, I reminded myself of my given f of x and what we calculated to be our f inverse of x, and then our formula we're going to use. So the first thing we want to do is if I plug in 1 over f prime, what is f inverse of x? We're going to plug that in right there. So I'm just going to say x cubed minus 2 over 5. Okay, now this says we got to go to our f prime, which is our first derivative of f. I did not pull that over previously, so we need to go back to that page where we calculated the derivative. Let me just toggle back for a minute. In part A, when we calculated the derivative, we got this value right here. So I'm going to pull my derivative over on this page so we have it there to look at. So now this one, let's be real careful with this. We just have our 1 here, so that's carried down. Now we want to go to the derivative function, the first derivative, and plug this in everywhere there's an x. So let me first of all write down, so I have a 5, 3, everywhere there's an x, let me put a parenthesis. Okay, it's ugly, but this one is just our entire numerator, and then our denominator is what I put in blue. So my blue is my f prime of x, okay, and then the red is when I substitute this value into the first derivative. Okay, and I think I was careful not to write any mistakes. So first of all, let's see what happens if we have this 5. This 5 is going to cancel. So then what about x cubed minus 2 plus 2? What happens there? So we're just going to get, those 2's will cancel. So we would just get x cubed. So 1 over 5 times 3x. What is the x cubed to the 2/3 power? Off to the side, x cubed raised to the 2/3 power would be power to a power multiply, so it would be 2 times 3 is 6, divided by 3 would just be x squared, so we would have this. And algebraically, let's multiply by the reciprocal, which would be times 3x squared over 5 times 3x squared over 5 in the numerator as well. Of course, the whole denominator cancels, and we're just going to be left with 3x squared over 5, which that would be our derivative of f inverse of x. Now, the, the algebra part is what you have to be really careful with in this example. Okay, so can we do a check right here? So if I have my f inverse of x that we calculated, and I took the derivative of this. Now I rewrote that as a 1/5 x cubed minus 2. Okay, if I took the derivative of this, my 1/5 is just out front. Okay, it's just 1/5. What is the derivative of this? 3x squared, right? And then if I simplified that, what do we get? 3x squared divided by 5. So this is kind of a check step. We could check, in which that was pretty easy. So you can check there.